Hi everyone, this is Jan 2 and Jan 1 from ArangoDB. I'm Jan 2, I'm the head of communications of ArangoDB, and today we have the first episode of our, hopefully a series of little videos where I get stuff explained from our core developers. So I want to learn as much as possible about technology, and today I've got Jan 1 with me, Jan Steemann, who is explaining complex queries at scale.
Hi everyone, my name is Jan. As we are both named Jan, my name is Jan 1 effectively in this talk. And thanks Jan 2 for the introduction. So I will take you and Jan 2 through this talk, which I prepared beforehand. And it's named Running Complex Queries in a Distributed System. And Jan 2, if you have any questions regarding this talk, regarding the matters that I discuss here, please interrupt me and ask them. Mm-hmm. So if you don't, I'll just go ahead with the explanations. And yeah, I'm happy to be interrupted by you, so just let me know.
Perfect. Thanks a lot for taking the time, and I would say we're good to get started.
Vale. Okay. So the motivation for this talk actually is that as a developer, especially as a database user, you are told like, okay, there is a specific trade-off. Whenever you select a database, or whenever you have to select a database for a project, you have to be aware of some trade-offs. So you can either pick like a highly available, scalable database, which normally boils down to any NoSQL database, or you can pick a database that supports complex queries, joins, and that has transactional guarantees. I try to put this into a picture, so you can either pick the database from the, I'd say, the right end of the spectrum, so any NoSQL database which will be highly available and scalable, or you could pick a traditional relational database which has like complex queries, joins, transactions, everything that you are used to from the like traditional relational world, but you cannot have both. That's what we've been told all the time, and I mean, yeah, it has made sense, this distinction, but the motivation for this talk is to show that this is not 100% true anymore, and that there are systems which actually are now placed somewhere else. So we still have these extremes, like we have traditional relational databases with all the functionalities that we need, but they are not highly available and not scalable. We still, of course, have these NoSQL databases, which are highly available and scalable, but do not have these complex querying functionalities and transactions. But nowadays, we also have highly available, scalable databases that also provide complex queries, joins, all this, and also partly transactional guarantees. So we have like a new class of databases, which I named NewSQL here. I don't care how actually this class of databases is named. It's just the marketing buzzword from my point of view. But anyway, they exist. So there are databases which now combine scalability, high availability, and transactional features and complex querying. And this is quite good because we as database users or developers have more choices nowadays.
Could you maybe fill me in? So where would ArangoDB fit in? Is it already the new SQL buzzword, or is it something on rather side of the spectrum?
I'd say ArangoDB is somewhere between the traditional NoSQL, so it provides high availability and scalability, but also provides complex queries and joins. So it's somewhere between NewSQL and NoSQL, I'd say.
Okay.
But these are just like marketing buzzwords. So ArangoDB has no SQL interface, but it has complex queries. Mm-hmm. And it has partly it has transactions. It's highly available and scalable, so it belongs somewhere near the bottom, I'd say.
All right.
So my agenda today. So the structure of this talk is I will give a quick introduction into distributed databases, what they actually are and how they work. Then there'll be a section about organizing queries in a distributed database, which will use ArangoDB as an example and some ArangoDB example queries. Then I have a section about distributed asset transactions, which will only touch how transactions are organized. I also have provided space for Q&A, Jan, so you can ask questions at the end if you want.
Perfect.
So some disclaimers up front. I will only talk about OLTP databases today, so I will not talk about Spark Hadoop or anything that like these databases where you load huge volumes of data and then query them, but do not change the data set that often. So I will concentrate on databases where you have like where your data is actually changed or can be changed while you're querying. Right?
Okay.
So, quick introduction to distributed databases. What actually is a distributed database? So, a distributed database is, it's more or less like a cluster of database nodes that work together as one database. So, you need that, for example, if the size of your data exceeds the capacity of one single server, then you need more than a single server. And you have more or less a set of database servers which you put together or chain together, and they work together as a single database. And obviously it's distributed because it's not only one machine, it's multiple machines. And with distributed, I do not mean that they are geographically distributed, like between multiple countries or stuff like that. Distributed can mean that these machines can sit in the same rack, in the same data center, but they're still different machines. So the data has to cross the border of a single database node.
Mm-hmm. Okay.
So distributed databases, so you normally have large data sets, and that means your overall data set will not fit on a single machine, but it has to be split. It has to be partitioned into smaller chunks, which are also called shards. And each shard or each part of the data lives on just a single node in this database cluster. And you do this, so you actually distribute your databases, or you actually have distributed databases, because by adding new nodes to the database, you can increase the database capacity and scale out. Quick example. So here I said we distribute the data set into smaller chunks, which are called shards. The squares here are actually my shards. So I have 3 database nodes, 3 database machines, which are named node A, B, and C. And I have 7 shards. So my whole data set is in these shards, and these shards are already distributed across 3 database nodes. So each of the database nodes is responsible for a part of the overall data. And I said, you do this, so you have actually a distributed database, so you're able to scale out. Let's check here. So node A has 2 shards, node B also has 2 shards, node C has 3 shards. It may already be overloaded, so because there's more shards than the other 2 nodes. But we said we can increase the capacity by adding a new node. So let's do it and add node D. So node D will add extra capacity to our database. So we can, not only can it take the one extra shard from node C, but it can also take one more shard. So now we can handle 8 shards, and if we add more nodes, we can handle even more shards. Just as a quick example, so adding nodes means more capacity to handle, to store your data or to run queries. So one motivation for having a distributed database is definitely to increase the capacity, or to be able to increase the capacity and scale out.
Okay, quick question from my side. So now I have sharded my data on different machines. But where is the difference I don't want to ask too much in one question, but where's the difference now in terms of transactions when you have when you could just imagine I have one server with several disks and maybe one disk on several servers. So what's the difference in terms of transactional guarantees? So why does it make a difference?
So I will touch that later.
Okay.
So actually there's a whole section on distributed transactions, which will come later.
All right.
This is just the simple introduction. But here, as you can already see, we have the data is residing on different machines or physically different machines. That means whenever we run a transaction, we need to organize this transaction across multiple machines, which is way different than running a transaction on just a single machine. Because here, obviously, we will have network communication involved for the transaction. So when we want to commit something or move data, like store data on different shards in a single transaction, then we will have network communication involved. We may have things like a node may go down, other nodes may stay up. We may have network partitions, all that. That all makes organizing distributed transactions way more complex than organizing them on a single machine.
Okay, got it.
Okay, so getting back to the original example, obviously it was oversimplified because we have each datum is only stored once. So we have these 3 nodes with 2 shards, and 3 shards. The problem is as we have more nodes or as we have multiple nodes in our cluster, the likelihood of one node being unavailable is actually there, and it's higher than with a single server. So at each time there may be like a node failure in our cluster. What do we do then? So now we have distributed our data across multiple servers. What if a node was actually down? How do we handle data loss? And every distributed database actually is confronted with this problem. So if your node goes down, then part of your data, and in this case here node B is down, it's unavailable. Part of your data, the 2 shards from node B are unavailable. So part of your data is actually lost. Obviously, that is something you don't want. And so distributed databases handle this here in a way that each datum is not only stored once, but it's stored at least twice. So instead of just saving the data in one shard, we are replicating the data to some other nodes. So in case a node goes down, for example, node B goes down, we have a copy of node B's shards on some replicas, or on some replica nodes. So some of the nodes are taking like the leadership for the shards, and some of the nodes are taking like the role of replicas for some shards, and that can be mixed. Like a node can be a leader for some shards and a follower or a replica for some other shards at the same time. So here in this case, so we have each datum is stored twice. So we have the shards and we have the replicas for the same shards. Now let's see what happens if our node goes down. So B goes down now. So that means all the shards of node B are unavailable, and all the replicas it stored are also unavailable. But this will only be for a very short time. Like this node is now down, and because in a distributed database, the nodes will talk to each other, or they will somehow communicate their statuses. The overall database will quickly find out that one node became unavailable. And in this point, or at this time, the database will be smart enough to promote one of the other nodes. And here, for example, we have node A and C that are remaining. It will promote some of the replica shards from node A and node C to be the new shard leaders. So we have backups of the data of node B. We had them on node A and C, and node A and C now take over the replicas of node A and C now take over the role of the shards of node B. So we have all our data back. It's more or less just a smooth switch over. So node A and C are now taking control and are handling the failure of node B. So we can continue with one node less and can handle the failure of the single node. And obviously, the more often we store, or the more replicas we have for each datum, the more node failures we can tolerate. Here, this example, we just have the original datum plus we have one replica, so we can handle one node failure. But if we stored more replicas, we could handle even more node failures. And in big clusters, you obviously want to have like higher safety, because it's likely that more than one node goes down at a time. So you will have more than one replica for each datum.
In all this, if I understood the agency right, all this cluster management and which machine is responsible for which shard, where to switch over, this is handled by the agency, correct?
In RenderDB, there's one place that more or less is the truth and or stores the truth about the current cluster situation and configuration, and that's named the agency. Okay. Which is also actually a replicated place, so it also has a backup of its own data. So in the RenderDB, these nodes, if one node goes down, it will be detected, and the other nodes would find out by consulting the agency about which nodes are still alive and what kind of responsibility they have. So in the RenderDB, everything would be communicated by this agency. In other databases, there may be other mechanisms, so the nodes may talk to each other directly.
Okay.
Right. So this doesn't really matter. It's just it's detected rather instantly that one node is down, and then the other nodes take over. Mm-hmm. And while a node is down, you will have a situation that some data may be unavailable, but I mean, the client application can retry then, and the data will be back online after a short period of time.
Okay, cool.
So it's not lost.
All right.
And obviously now this year, once we've lost one node, we promoted some of the replicas to become the new shard leaders. So that was the previous slide. I'm going back now. So here, as you can see, we have like 7 primary shards. So we have all the data available for querying, but we only have 5 replicas because 2 of the replicas we had to promote to become new shard leaders, right? So at the moment we don't have enough replicas, but when this happens, this is also detected instantly, and then new replicas are seeded. So we are getting back to a situation where for every shard we have at least 1 replica, or the configured number of replicas.
Okay.
So it will more or less heal itself and handle the failover like gracefully. And as I said, we can handle as many node failures as we have, like replicas. And this example, to keep it simple, uses just a single replica. Okay, so that was the introduction to how actually distributed databases work. Like very quick. I mean, obviously you can talk about like a day about this. Just a quick intro, and now I want to talk a bit more about how actually you organize complex queries in a distributed database. So how is that actually done? So how can you actually query data out of it? It's actually not so simple. But I mean, compared to the asset transaction part, I think this is relatively easy to understand still. So the difference to a single server database query is that in a distributed database, you will have network communication, right? So your data is not only or not necessarily on a single node, it can be stored on multiple nodes. And if I run a query that wants to query from multiple nodes, I mean, somehow these nodes have to communicate and ship the data across. So a typical distributed query will involve multiple nodes and will have communication between these nodes. And normally there is one coordinating node for each query, which then is responsible for like fetching the data from other nodes. It needs to trigger the other nodes and tell the other nodes, okay, please give me this data from these shards. It may also trigger data processing on the other nodes. It needs to put the responses it gets from the other nodes together into a single response, because normally a client application will run a query and expects a single response back. It doesn't expect responses from multiple servers. It wants a single response, an aggregate response. So this is also our query coordinating node is also responsible for that, putting things together from multiple shards and sending an aggregated result back to the client. And obviously this coordinating node is also responsible for telling the other nodes, okay, this query is done, please free all the resources, next query, more or less. So we have some sort of coordinating role in a distributed database. And a very quick example here. Let's say we have a client application. This is the icon on the bottom left. So this client application sends a query to our coordinator node, which is at the bottom in the middle. So it gets a query. It can be a query string, any SQL, or it can be an AQL query, and anything that more or less what actually composes a query in that specific database. So the coordinator node gets this query request. This coordinator node is then responsible for contacting the actual data nodes. So the nodes that host the shard data, and actually needs to query them and gets the data back from them and puts everything together into a single aggregated query result. And when it's done, it will tell the database nodes or the data nodes, okay, this query is done, please shut down, or please free all your resources, we are done with this. Right? So this is the difference. We have this coordinating node, and this coordinating node is more or less orchestrating the whole query. And as a consequence, so we have communication between the nodes. So we have the coordinating node, and we have the 3 data nodes, and they need to talk to each other. So that means there will be network round trips between them. And network round trips, as you all know, they cause latency. If you have just a single server, there is no need to communicate with other database nodes. It will just be instant. Fetching data is just instant if it's already in RAM. But in distributed database, fetching data means you have a network round trip to another node. This node needs to provide the data and send the data back. So this is a lot of overhead compared to a single server. But it's unavoidable, so you cannot get away without that. But you have to take this into consideration. So whenever you run a distributed query, you want to have as less inter-node communication as possible, because every communication means latency. So you want to do as few requests between these nodes as possible. So what you actually want to do is, whenever you get a query, you try to optimize that, or your database will try to optimize that and restrict the query to as few shards as actually possible. Of course, it's better to contact just a single shard or a single server than multiple shards on multiple servers, because that will mean contacting just a single server means, just one request instead of multiple. You obviously want to push filter conditions, like where conditions and everything, or aggregation commands, also on the data nodes, because this may reduce the amount of data these data nodes have to send back to the coordinating node, right? And the less data they send, the quicker it will run. So you not only want to minimize the number of network round trips, but also want to minimize the amount of data that has to be shipped over the network. Because network can also be a bottleneck, especially if your database is like geographically distributed. And what can also be done is like, you have this one coordinator node in this example, and you have multiple data nodes that actually have the data. And a distributed database actually allows querying them all in parallel, right? So you have the single coordinator node, which is a bottleneck, or is a bottleneck in a query, or can be a bottleneck, but you can parallelize the amount of work on your data nodes, because I'm going back now. These three data nodes can run stuff in parallel, whereas on the coordinator, we have to somehow serialize the work. But the things above, they can work in parallel. They can query data, they can filter data, they can aggregate data, all in parallel. So now I'll talk a bit about, more specifically about ArangoDB. So everything that I said until here was more or less like database agnostic. So any distributed database can be organized like that. But now I'll be talking a bit more about ArangoDB specifically. ArangoDB, if you don't know it yet, it's a multi-model NoSQL database. Multi-model means it supports documents, graphs, and key values, all in one engine and with one single query language. ArangoDB can be run as a single server database or as a distributed database with multiple nodes, which we then call simply the cluster. As I said, ArangoDB has a query language. It's named AQL for ArangoDB query language. It's somehow similar to SQL, so it has the same purpose as SQL, but it has a different syntax. But I promise, if you know SQL, then you will understand AQL pretty fast. So it has the same concepts, only a different wording. So here's a quick example for a query with ArangoDB. I put the equivalent SQL actually on the slides to make it easier for SQL users to transition and to understand. But let's first start with the ArangoDB query. So we are querying all the data from a collection named users. And a collection is actually, in SQL terms, it's the same as a table. Just think of it as it would be a table. So we are querying from a collection named users, and we want all these users that have a specific property, so a specific column or attribute, set to the value of true. So here we are getting all the users which have an active attribute of true and return them. That means let's get all the data of these users which are active. The equivalent SQL query is at the middle of that slide too, and should be easy to understand. So what will happen here in this query is that in ArangoDB and several other distributed databases is the coordinating node will find this filter and will push the filter condition down to the shards. That means the shards will only return matching data. I mean, obviously, if we do it like this, so obviously we could have the data nodes return all the data from the user's collection, right, and have the coordinator filter out everything that we don't want, right? So the data nodes could give us actually the whole contents of the user's collection. But let's say the filter is very selective. So the filter filters out a lot of records and only returns a small fraction. Only a small fraction of the users actually satisfy the filter criteria. Then it's much better to run the filtering on the shards, on the data nodes already. That means we have just a very small amount of data that needs to be transferred from the data nodes to the coordinator. Right? So one optimization that most of the distributed databases, including Arango, are doing is they're pushing the filter conditions to the shards close to the data. So the data nodes can filter out everything that is not needed and don't have to send this massive amount of users over the network that we actually don't want at all.
So basically we're using the whole resources that we have in the cluster for computing the end result.
Yes, so we have to, because let's say users is a sharded collection. So we have at least 3 nodes that have data for this collection, right? Okay. So we have to ask 3 nodes. Because the data for users can be on any of these 3 nodes or on all of 3. And what we don't want is that all of these nodes return us all their users and have the coordinator like filter out the ones that we don't want.
Okay, so the coordinator knows, let's say the user collection is sharded to 2 machines. Mm-hmm. The coordinator knows this and just sends the filter request or the request to these 2 nodes, not to everyone, of course.
Yes, obviously. So the first thing the coordinator will do is find out which nodes it actually has to contact, and it will only contact the nodes which actually have data for the users collection. Okay. Yeah. In my example, these are already 3 nodes. I mean, if we had 10 nodes and the users collection would only have data residing on 3 nodes, then obviously the coordinator will still need to contact just like the 3 nodes and not 10. Okay. So that will always be done. But it will also push this filter condition, and the filter condition is here u.active equals true. It will also push that upwards, so that all the shards will only give us like the matching data already.
Okay.
Instead of returning all the user data over the network and the coordinator filtering out the ones that we don't want.
Okay, understood.
So we push this filter condition up. Another thing that's now getting a bit closer to your question that you just asked. Let's say we have a query that filters on our shard key attribute, and shard key attribute actually means the data is distributed in the cluster by some sort of we have a sharding mechanism, and it will put each record, so each document or each row of data, it will put onto a single shard plus the replicas. But each row will reside on just one shard. And how this is distributed is decided by the by what attribute the data is actually sharded. And in ArangoDB, the default sharding attribute is actually _key. That means the database will look at the _key attribute of each incoming document. And yeah, depending on the value of the key, it will move it to one specific shard. There's a hash function applied on the value, like here it's Jan Steemann is the value. This value would be hashed, and from this hash, the actual shard would be determined. So we can simply determine, okay, if the shard key attribute value is like Jan Steemann, then it can only be one specific shard. It cannot be on the other 2 shards. Okay. So this is also an optimization that is normally done and that ArangoDB will do. If we have this query here, and the SQL equivalent is like in the middle again, the coordinator will detect that and will only ask that one specific shard for the data. Because now it knows, okay, this collection users, it has 3 shards, but I know by it's sharded by _key, that's the shard key attribute, and I know the value of _key for this particular query, so I only need to fetch data from this one shard. So now we are not contacting 3 database nodes, but 1 database node. So we save 2 requests, which actually can mean a lot, right? If we run thousands of these queries at a second or thousands of these queries, like we save a lot of traffic and a lot of work. Obviously, we also want to push the filter condition up to the data nodes, as in the previous example. So the data node here will only return a single row or single document instead of just everything. We have the coordinator filter it out. So this will restrict the query to just returning a single record over the network. And all this is done automatically. Another example for this is what we can do is, and basically it boils down to mostly the same. So let's say we want to have all the users now, so we will still have to contact all the 3 shards, but we want to sort them by their name, and we only want their names back. We don't want the complete data set of users, we only want the users' names. SQL query in the middle again should be trivial to understand. What's happening here then is, first of all, we have this projection, so we only return u.name. So the shards, the data nodes, will only return the names of users now, instead of the whole data set, which will reduce the amount of data they have to transfer by lot. Right? We don't have complete records, we just have names that will be returned. But additionally, we have a sort instruction. And the sort instruction here, it can be sent to all these data nodes again. So we can sort the users by their names on each data node independently. So each data node can now run the sorting already and return a sorted result. That means each shard will return us a perfectly sorted result. The only problem is that the overall result of the 3 shards will not be totally sorted. So we don't have a total order, we just have 3 locally sorted results. So now the coordinator needs to bring this in order again. But as all the 3 results are already sorted, the coordinator can apply a simple merge sort and doesn't have to sort let's make an example. So let's say we have 3 million users, 1 on each shard, right? If we let the coordinator sort everything, then it would get like 3 million rows from the shards, which it would need to sort, right? But if we have the shards return these already sorted sub-results, then the coordinator just needs to look at 3 streams of data and just and they're already in order. So it only has to look at the top of the streams at one record at a time and compare which one is the next to push into the overall result. So this merge sort doesn't require to have everything in main memory and to sort that, which would, like in distributed database, the amounts of data can be huge. Like let's say you have like 100 shards, then you may get a lot more data back. And to have all that sorted on the coordinator would be like overwhelming. So what we can do here is have all the shards already pre-sort their fraction of the data. So the coordinator only needs to do less expensive merge sort.
Okay, and this is all done automatically by the coordinator, so the user doesn't have to specify anything. This is automatic, right?
In the RangoDB it is. So we have this query optimizer that will more or less exploit this, exploit that and push the sorting to the shards. There's some other databases which can also do that. I think, as far as I know, Cockroach can do this as well. Not sure about any others, but I mean, technically, that's a way of reducing the amount of work.
Okay.
Another thing is aggregation. So this is also a bit similar. Let's say we want to query all the users and group them like by their year of date born. So each user is born in a specific year. So we now want these years returned, like the year of birth, and count how many users actually fall into each year of birth. SQL query is again here, the AQL equivalent is on top. What we can do here is also, we can try to push the aggregation to the data nodes. Same as with sorting and with the filtering, right? And it makes a lot of sense because actually, if we return, or if we have the data nodes return the individual users again, like we would get 3 million users, and we would have to do all the aggregation on the coordinator. We would have to form the groups for the years of birth on the coordinator over 3 million records. What we can do here with this query is we can run the aggregation, like grouping by date of birth. We can run this on the data shards again, on the data nodes. Because counting, what we want is, we want to have, for each year of birth, we want to have one result which just returns us the number of users that were born in this year. And we can do this on all the shards separately. Obviously, then we get 3 results for all the years of birth, and we need to aggregate them again on the coordinator. So we have one level of aggregation on the data nodes, and we have another aggregation of level of aggregation on the coordinator. So here, the coordinator will push the first level of aggregation to the shards and will then aggregate the aggregates from the shards, because the shards will already produce aggregates. Right, and let's assume we have 3 million users, and we have like 100 distinct years of birth, right? If we have the shards return just the user data and have the coordinator aggregate that would mean the coordinator will need to like aggregate 3 million rows.
Yeah.
If we push the first aggregation to the shards, each shard will only return 100 rows because it has already aggregated by year of birth. So each shard will return 100 rows. So what's transferred actually is then like 300 rows, 3 times 100. So the coordinator will only need to process 300 rows instead of 3 million.
So that means with the more data that I store in my cluster, the advantage of this of pushing it down to the database to the data nodes increases, right?
Yes, because I mean the idea behind an aggregation is normally that it makes the data smaller than before. So aggregation more or less boils data down to a smaller value actually. Instead of having like a million users to look at or a million users to like return, we would just have 100 different rows with each year of birth once, and with a counter for each.
Okay.
This is a relatively small data set. And if we only transfer this data set between the coordinator and the data nodes, it will be a lot less traffic than transferring like a million users, right? But still the coordinator now needs to, I mean, it gets 3 aggregates already. It needs to sum them together, but its good count is a commutative operation. So it can simply sum these counts together at the lowest level, and then it will have the correct result. This is not possible for everything, for every aggregation operation, but for like min-max count, these things are actually commutative, so the coordinator can actually apply this optimization and push some level of aggregation up to the data nodes.
Okay, understood.
Right. So this saves a lot of processing, actually processing work, and also a lot of communication. Last example to show how queries can be organized in a distributed database is a join. So far we just talked about a single collection, and this is just fine because there's several queries which only affect a single collection. But let's say we have multiple collections now, and actually it's possible to run joins and queries on multiple collections even in a distributed database. It's just more processing work. Let's say here we want to join not only the users, so we have these users still, but we want to join each user with the purchases they have made. And just a simple example query. Focus on the SQL query if you don't understand AQL yet. It's just a simple joining the users to the purchases. So we have 2 collections here, or 2 tables, users and purchases. And as usual, we have to define how to organize this query. So we still have our coordinator, which will get the initial query from the client application. And the coordinator now has to figure out what to do. We have 2 collections now, so it's not obvious if it should go to the users collection first or to the purchases collection first. So the query optimizer will kick in and figure out what is the optimal plan here. And in this case, it has decided, okay, I need to go to the purchases collection first. So the coordinator will now reach out to the data nodes that host the data of the purchases collection. Right? This is the thing from the bottom right to the 2 nodes above it. Let's say purchases has just 2 shards or 2 data nodes which are affected or host the data. So the coordinator needs to reach out to these data nodes. So they can provide all the data for purchases, which is great. But now we also need to join the purchases with the users' data. So what will happen here is that the data nodes that are responsible for purchases, they have to reach out again. And in the RangoDB, they will reach out to a coordinator again. And this coordinator part is then responsible for fetching the data of the users collection, because we need to join that later on. So we will not only have one reaching out from the coordinator to the collection nodes or to the data nodes, we have two levels of reaching out, right?
Is this so? I'm just a bit unsure if I understand the schema correctly. So is this everything happening in parallel, or is this sequential? Because if I follow the schema, first coordinates the first coordinator, then goes to the data nodes, then to the coordinator back again, and then to the other type of or the other data nodes storing the users.
So in ArangleDB it will be like yeah, okay. So the diagram is probably not that adequate. So actually, the coordinator will first contact the two nodes above it, which have the data for purchases, and they will instantly reach out to the nodes above themselves, or to the node above themselves, to fetch data for the users. Okay. So that they will, and technically on the low level, I mean, we have these two data nodes. They will produce like 1,000 results each from the purchases collection. Mm-hmm. And for each of these 1,000 results, they will need to apply the join operation now.
Okay.
And to run the join operation, they will once reach out to the node above it, which will provide them with data for the users collection. So they will now issue a request above and request data for the users collection. So they will get 1,000 results for the users collection now, mm-hmm. and apply the join locally. And if there's no more data from above, it will just stop at this point. But I mean, there may be more data from above, so they may need to fetch more data from the users collection to join like with everything.
Okay.
So they will eventually like query more data and more data and more data from above, because I mean, they need to join with the whole table. Obviously, they can use all this query can obviously use indexes if they're the adequate indexes. So it actually only will fetch as much data as needed, and if things are indexed, then indexes will be used.
Okay.
But in general, we don't know how many matching users there are. So there may be one matching user, there may be thousands matching users. We don't know. So it will just fetch as many as there are and matching, then execute the join and return the joined data back to the coordinator.
Okay, understood. Until
there's no more data. Mm-hmm. But effectively, as you can see, it's already quite complex here. If you add a third table, it's getting even more complex, and I already ran out of space for this diagram, and I cannot really put this into a diagram. But effectively, you can put together as many collections as you want. But any join here means network communication, and that's unavoidable because the data is located at different sites and it has to be brought together. So you will have network communication, and that's also the reason why a query in a distributed database can actually be a lot slower than a query in a local database, because the data is distributed and it's somehow unavoidable. Mm-hmm. If you have different locations for your data, then you have to fetch it and bring it together. And that's, I mean, yeah, you cannot be faster than speed of light, actually.
Okay.
Okay, so that's how like data retrieval queries can be organized in distributed database. And as mentioned, there are already databases that can do these kinds of queries. For example, ArangleDB is one. It can do all these join operations between multiple collections on different servers. CockroachDB is another example that can do all this. And I mean, over time, I think there will be more of these distributed databases that support that distributed complex querying functionality. I think there's some clear trend towards this. Google Spanner, Google Cloud Spanner is also an example of the database that can do queries like this. Okay, so the next question, or sorry, next section is about distributed ACID transactions.
Maybe one quick question before I forget it, and maybe someone else is also interested in that. So we said that if you have multiple collections and you shard it to multiple nodes, then you can't avoid network latency when doing join operations or maybe complex filtering and all that stuff. Mm-hmm. Are there, I mean, I know about the satellite collection feature of ArangleDB, so I also know that there are solutions on how you can reduce the network latency of those complex queries. Is this something we will discuss later, or should we maybe share a few thoughts about that?
We can do it right now because I haven't prepared any slides specifically about that. So let's cover it now. So in ArangleDB, you said we have the satellite collections. So let me quickly talk about that. So the satellite collections in ArangleDB are a feature that more or less, if you have like a collection that is used very often in joins or whatever, you can have the data of that collection residing on all the shards. So it's actually the data of that collection is copied to all the shards, which means you can do something like a local join, right? So wherever your data is, a copy of that satellite collection data will also be there. So you can join locally. But it's also, I mean, that's also the obvious restriction of the satellite collections. They can only have, they only work for a small amount of data, because if you copy their data to all the shards to join locally, you can only do it with a collection that has not so much data.
Yeah.
So, yeah, I mean, you're actually having a distributed database because you can have massive amounts of data, and your satellite collection is copied to every single node. So it must be a relatively small collection. And then it will work and you can run local joins, but it will not work in the general case where you have like data that doesn't fit on a single server, then you couldn't use that.
Okay, yeah, makes sense.
Right.
Okay.
There's also other things that we are currently looking at ArangleDB. So we want to like optimize some sort of queries there where we actually know that data is that data for the collections in the query is on the same node, and we want to leverage that knowledge to more or less run like shard local joins. We're not yet there, but we are investigating in this direction.
Okay.
And what was the other thing that you mentioned? I already forgot.
I think that was it.
Well,
I can't remember. If it pops up again, I will just ask again.
Okay. Valid. So yeah, we've covered how to get data out of a distributed database and how to actually organize that. Now let's focus a bit on how to get data in. But I mean, this section is about distributed asset transaction. That's not only write operations, but I mean, the write operation is actually much more interesting. So distributed asset transactions, why do we actually want them? I mean, in the first slide that I showed was, I spoke of this trade-off between like NoSQL databases and the traditional relational ones. And I said, okay, the relational databases, they all have transactions, but the NoSQL ones, they don't have transactions. And actually the transactions were left away in NoSQL databases for a good reason. Transactions are extremely complex to organize in a distributed database. So all the NoSQL databases of the that were first there, they left them intentionally away. So they said, okay, you can use this NoSQL database to scale out and have high availability, but you cannot have transactions at the same time because they simply don't scale. But actually, as a database user or as a developer, I actually want transactions because transactions, they make developers' life so much easier. A transaction means more or less that I can put multiple operations into one atomic unit of work and only more or less commit this work if all the operations succeeded. So I have multiple data items that I want to read and or write, and only if all the operations succeeded, my transaction will be marked as successful and be done. If anything goes wrong in between, my transaction will automatically be rolled back by the database. That's more or less the key feature of a transaction. So if something goes wrong, nothing has happened, it's executed in all or nothing fashion. That's also called this atomicity principle of the asset transaction. So the A in asset is for atomicity. That's quite nice. So if anything goes wrong, the database will clean up. If the server goes down, if anything crashes, anybody modifies the same data at the same time, the database will take care about that, and my transaction has never actually happened, and I don't need to bookkeep anything and need to clean it up. The database will do all this. This is what a transaction is actually for, and it makes developers' lives so much easier. The problem is, yeah, most of the NoSQL databases, they don't provide transactions. So what do we do? So actually, Nowadays, there are some databases, which some distributed databases at least, with transactions. So all the single server databases, they often provide transactions. Let's put it like this. So all the relational databases, they have transactions. ArangoDB, as a single server database, provides ACID transactions as well. But for distributed databases, there's a lot less databases that actually have transactions. So Google Cloud Spanner is actually one of them. They published a paper on how to run distributed transactions in 2012, I think. So that's a system that was developed and used at Google internally. And they came out with it as a public service in 2017. They provide distributed transactions on a, like, let's say, planet scale database, but it's running on Google's data center infrastructure. So if you want to use it, you have to more or less buy in. It's a database as a service. It's not something that you can download and install and run. CockroachDB is, to put it simple, it's something like the open source clone of Google Cloud Spanner. So they reused a lot of the concepts of Google Cloud Spanner, or Google Spanner as it was named at that time, and provide some open source database which you can actually download and use on your own premises. They provide distributed transactions. FoundationDB is another example. They provide distributed transactions. They have a quite interesting history. So they were quite, they gained a lot of attraction, like I'd say 2 or 3 years ago. Then were bought by Apple and taken from the market. And recently they were open sourced, or the product was open sourced again. And yeah, I still have to look into what has changed recently and what they actually do. But they also claim to have distributed transactions, distributed ACID transactions. FaunaDB is some closed source product which also provides distributed ACID transactions right now. And surprisingly, even MongoDB has announced support for distributed ACID transactions. For the next version, which will be 4.0, they will only have transactions on non-sharded collections, so they're not actually distributed. But they already announced support for distributed ACID transactions for like 4.2 or I don't know, some future versions. It's not released yet, so we cannot really judge that and how this actually works. But at least it's announced, and there's lots of movements in this sector of the market. ArangoDB has single server ACID transactions. And at the moment, we do not have distributed ACID transactions, but we are investigating in this area as well. And we are looking into how to get there. That's our current state. It's actually not so easy to implement them. Otherwise, I think all of these databases would have done that. So it requires careful work, actually, and it's a complex matter, as you will see soon. So now I will go through these. This section is about ACID transactions. I will now go through these ACID principles in detail and how they actually can be organized in a distributed database. First thing to start with actually is then the atomicity, which is the A in ACID. The problem is that in a distributed database, any transaction may make modifications not only on one node, but on multiple nodes, on different nodes. So let's say you write a record. You don't only write it on a single machine, but you may write the next record on a different machine, or on a third machine, or on a fourth machine. So your transaction may involve a lot of modifications which affect multiple machines. So so you have any number of machines involved in your transaction, not a single one. The problem is these modifications that are done in your transaction, they need to be ineffective until your transaction actually commits. So nobody must see the modifications you're doing in your transaction until the transaction is committed. But they are on different machines already. So you have deployed them to these different machines, but they're ineffective and hidden. But when your transaction commits, all your changes must become visible instantly at the very same time on all the machines. So all the machines now, like at the flip of a switch, need to see your modifications. How do you actually do this? If you have like network communication involved, and you have you have a network in between, and the network may actually also fail. So the network may be unavailable or have partitions or everything like this. So how is it actually done? So how this is actually organized is that a distributed database normally stores for each transaction a status. So whenever you start a transaction, we'll like insert it into some section of the key space. And so for example, you start transaction T2. Each transaction has just an identifier. Let's say you start transaction T2. Then the database will simply write a record to the key space, to some internal part of the key space, and say, okay, the transaction T2 is in status pending. We'll simply store this information somewhere. And obviously, as we've learned in the very first slides, we have replication. That means it will not only store it there in this part of the key space, it will also replicate this value to somewhere else. So let's say one server goes down, you still have stored the status of T2 somewhere else. So you have a replica of that. So the data is not lost. If a node goes down, it's still there. So let's say we said T2 is now pending. And whenever a transaction commits or gets aborted, we simply update that transaction's status key and write something into it like this transaction is now committed or aborted, right? Mm-hmm. So a transaction commit is actually like writing a value to the database and overwriting that transaction's status key with a new value like committed, aborted, mm-hmm. whatever. And the good thing is here that this writing of a key is an atomic operation. So this is something like that a database can organize atomically. And this will actually, together with some other things I will show, will make sure that your transaction commits are actually atomic. So if you commit something, it's an atomic operation. And all the things are visible at the very same time. And they stay ineffective until actually it's committed. Okay. Right? But you need this one place, more or less the place of truth where your transaction status is, where you can look up and check, is this transaction actually committed or is it not? And this is by just storing the transaction status in a private section of the key space under a single key. But we'll revisit that later. So one of the other things in ACID, the C actually, is consistency. What we need to do is, first of all, we need to make sure that we somehow get the writes to a single shard or actually to a single key into some specific order. Let's say we have multiple machines that or on all machines you get the request to overwrite the data of a specific key in the key range, right? Mm-hmm. And so you have concurrent requests going on to change the value of a specific key. Which of these requests will actually win? Let's say the one write will update the key value to 10 and the other will update it to 42. Mm-hmm. What actually will happen? So what we need to do is, in a distributed database that has consistency, we want to get these writes into some order, right? And we want to have the same order for all the machines. Like if we write on the shard for that key, we need to determine an order for these writes, which one is first, which one is after that. And if we replicate these writes, because all the writes need to be replicated, because if the server goes down, we still need to have a backup. Mm-hmm. The replication must be in the same order as the original writes. If we write in a different order, we would not have consistency between the shards and the replicas. So what we do is for each shard, we have a leader for each shard. We determine who or which server is actually the leader for a specific shard. And all the writes for a shard go to this specific leader for the shard and only to the leader. Right? Mm-hmm. So the leader can get all the writes for a shard and for a specific key in the shard into some order by just serializing them, and the leader can then organize the replication. And the replication will be in the exact same order that the writes are happening on the leader. That means our replicas are now exact copies of our leaders, of the leader data, actually. Mm-hmm. So the replica will not get out of sync. It may lag behind, right? But it will not have different data. It may only be behind, then it's not up to date enough. But I mean, if it's up to date, then it will have the same data as the leader and will be an exact copy, which is nice because that allows us to switch over between actually the leader and the replica. Okay, understood. So a replica can take over at any time. And the good thing is that we can always ask the leader for a shard about the current state of data. So the leader always knows. If we would allow writing to all shards at the very same time for the same key, we would never know which one has the latest, which is the source of truth, which one is the latest, right?
Mm-hmm.
So here's a quick example. So let's say we have two client requests going on in parallel. The one writes the key amount to a value of 10, and the other writes the key amount to a value of 42 at the very same time. If we would allow this and have each node accept that write request and then replicate it from there, then we would have chaos. Like depending on which node we would ask, we would get either 10 or 42 back.
Mm-hmm.
But now, if we do it like this, so any write request for a specific key needs to go to the leader shard of that. Then we can get these things into an order. And here the leader has put these writes into an order, like it executes the 10 operation first and then the 42 operation, and will replicate this in exactly this order. So the replica shard on the right will have the same data as the leader, and it will not have it will not get the 42 first and then the 10. Mm-hmm. Right? So it will get data in the same order. That also means, okay, this replica can take over anytime. It will have the same data as the leader, only that it may be behind, but apart from that, it's the same. And also it means if we write everything for a specific key to a leader, it means this leader can detect the conflicts locally. So if two transactions are going on at the very same time and modify the same data, this will be a write conflict. If we write on different machines, like let's say every machine can take these writes and execute them, then we couldn't detect the conflict easily because the writes may be executed on different machines and we cannot detect conflict. But by directing everything to the designated leader for a shard, we can have conflict detection locally, and we will always know if another transaction is ongoing that modifies the exact same key because we have the data on this one machine, right? So we can do also the conflict detection here. And this means for anything that requires consistency, we need to have, we need to serialize the writes for a specific shard on the leader of that shard.
Okay.
Yeah, so the shard leadership, as I said, it's important for consistency, but it can change over time, right? So let's say we have, in my original example, we had these three nodes, A, B, and C. Let's say node B goes down and node B was the leader for some shards. Effectively, the shard leadership will change after the node goes down and will be handed over to some other nodes, to the remaining nodes, right? So let's say node A and node B, node A and node C take over the leadership for some of the shards, right? Mm-hmm. So shard leadership is more or less floating. The problem is if you have a cluster of database servers or database nodes, they have to agree on who is actually the current leader for all these shards. Like you may have like 100 machines and thousands of shards, and the leadership may change over time. But all the nodes have to agree who is the current leader for a shard, because they have to write to the same shards in order to guarantee that consistency. So what you will need in distributed database is something that is named a consensus protocol, right? And the consensus protocol is something like the nodes in the cluster, they will talk to each other, or in the ArangoDB, they will talk to our agency, which is the place where everybody stores or where the cluster has its central configuration. Mm-hmm. And all the nodes in the cluster, they need to communicate and agree on who is the current shard leader for each of the shards. So that in case, if everything fails or everything changes, all the nodes in the cluster still have a consistent view of who is actually the leader for which shard and who are the replicas. It makes no sense if one node goes down and then two of the other nodes think they are the leader for the same shard.
Sure.
Then everything would be broken because then the writes would go to any of these nodes and then we would have like inconsistencies. So they have to agree on who's the next leader or the new leader for the shard. And we can ensure this by using a consensus protocol. And other databases do this too. This is not ArangoDB specific. So in use are actually Paxos and Raft, which are the most commonly used consensus protocols in distributed databases nowadays, I think. So for example, Google Cloud Spanner internally seems to use Paxos. Cockroach and ArangoDB use Raft. And Raft and Paxos, they both provide guarantees that whenever something goes wrong, so in the face of failure or network partitions or anything, you can still get to a consistent state, given that a majority of your nodes in the cluster can still communicate with each other. Let's say you have 5 nodes in your cluster and 2 fail, then Paxos and Raft will guarantee that these 3 remaining nodes can still agree on something if they are still available and can communicate among each other. And even if there's a network partition, so you have a partition like 3 nodes are on one side of the partition and 2 nodes are on the other side, they can still, or these protocols still ensure that you will have, that it will still work.
Okay, what happens if, maybe a stupid question, but what happens if from my 5 nodes, 3 fail and I only have 2 nodes?
Okay, so most of these things are like, so you know the SCAP theorem?
Yeah.
Like consistency, availability, and partition tolerance.
Yeah.
So ArrangoDB is actually, it is CP. So it has consistency and partition tolerance, but it will sacrifice availability if too many nodes go down, or if there's actually, if a majority of your nodes is down, then ArrangoDB will this Paxos and Raft, they will not allow getting to a consensus. So effectively, that means you will reach no consensus, and then effectively your cluster becomes unavailable.
Okay, so to ensure that the consistency of my data is ensured. Okay.
Yes, so it will give up availability then, and most other things. I mean, even Google Cloud Spanner, they will sacrifice availability. So if a majority of the nodes would go down or would be unavailable, then they would give up availability. Okay, right. But in practice, this doesn't happen for them because they have this like the data center infrastructure is like so fancy that in practice it will never happen. But in theory, it may still happen. Okay, right. And I think this is true for most of the. I mean, a database with ACID transaction needs to provide consistency, right? And I mean, I can't think of another case when I think it always will need to give up availability then. Okay, some case.
Understood.
Okay, so all of these databases, including Arango, they will use some sort of consensus protocol behind the scenes to agree on what the current state of the cluster is, which nodes have which roles, and which nodes are actually the leaders for which charts, and so on. So this is all happening magically in the background by using these consistency or this consensus protocols, more or less. And in ArangoDB, the part that talks like Raft is the agency. So the agency internally talks Raft. So multiple agency nodes can still agree on a consistent view of the cluster, and also can take over if one node goes down. Then we still have these backups, and these backups are guaranteed to be consistent by using this consensus protocol. And that's obviously a requirement that you need for having a distributed database with consistent transactions. Another thing that's very interesting is you need to order transactions somehow in a distributed database, because you want consistency, right? And you may have transactions that modify the same data at the very same time, right? Like in this previous example, we had this 2 transactions, and the one changed the amount value to 10 and the other to 42. If they run at the very same time, you have to put them into an unambiguous order, right? You have to make sure that the order of these transactions can be told apart. The one was before the other. Or you need to have some happens before relationships somehow. And this is actually quite difficult, because think of a distributed database. A distributed database has transactions that can start at any node, right? And can modify like data on any node while the transaction is ongoing. Let's say a transaction starts on node A and then modifies data on node B and then C. But another transaction may start on node D and then modify data on node A and then C and then B, or whatever. Okay. So you don't ever know what will happen next. But these transactions may clearly overlap, and at some point they may touch the same key and override the same key. or one transaction may read the key and the other may write the key, and then you have to determine which version of the key the transaction can actually see, right? Okay. Because they're running concurrently, and now you have to do something like, if they modify the same key concurrently, you have to do some sort of tie breaking, because they cannot obviously modify the same key at the very same time, because that would cause a data loss or anomaly. Mm-hmm. So you have to prevent this from happening. And what you need for that is to have an unambiguous global order of the transactions, mm-hmm. regardless of where they started and what keys they actually touch. And this is really hard because, they are originating on different servers. And at some point on any server, a transaction can start and it may then eventually get to the same key where another transaction is already operating on. Mm-hmm. And that you have to find out. And then you have to do something and check which transaction now actually has to or can go on and which needs to be aborted.
Okay, so not everybody has an atomic clock in their data center like Google does. So defining which transaction came in first is then hard to determine, correct?
It's hard to determine, but you have to do it somehow because you have to have this order for the consistency. And one thing to do this obviously is to use timestamps for transactions. So the obvious solution is every transaction that is started will get some timestamp. Mm-hmm. So the current time, transaction starts or transaction begin means take the current time and mark this for the transaction and store this for the transaction when we write this transaction's key somewhere. So we're not only writing transaction T2 is pending, but it was started at this specific timestamp. Mm-hmm. So we save that at a place, and all the other places can check at what point the transaction was started. And if the transaction commits, we will use just this timestamp that we created at transaction start and use that as the commit timestamp, right? That means if we have a transaction that just does nothing, that's just begun and committed, it will have the same timestamp. Now, if a transaction modifies some data in between, and that's normally the case, then a transaction will always modify some or read or modify some data in between. There will actually some time will pass between all these operations. So begin and commit are actually a bit apart time-wise. Mm-hmm. But we still can use the same timestamp for the transaction commit if we don't have any conflicts with other transactions, right? So we can still use this, but we need to do conflict detection everywhere. And whenever we find some reads or writes that touch the same records, we need to figure out, we need to look at our current transaction and check its timestamp. Mm-hmm. And we need to find the timestamp of the other transaction, and then we need to bring them into some order. Okay. Obviously, for two timestamps, we can use a comparison like less than or greater than or whatever, because it's just numbers, right? So we can simply compare the timestamps, and the transaction with the lower timestamp has happened before the one with the higher timestamp. That's the rule, basically.
Okay, makes sense.
But there's the one obvious problem that you just mentioned before. That is, we can have clock skew. That means if we have different nodes in our database cluster, they all have like different clocks, or they all have clocks, and the clocks can be apart. There's no guarantee, even if we use NTP or whatever to sync the clocks, there is no guarantee that they're actually in sync. Mm-hmm. So we cannot reliably tell, if we look at timestamps created by two different nodes, we cannot reliably tell which timestamp is actually earlier or which one is later, because there is still this clock skew, right? Mm-hmm. So it's like unsafe to compare these timestamps or two timestamps from different machines. But as usual, part of the problem can be just defined away, or most of the problem can be defined away. Okay. And how this is normally done, and how like Google for Cloud Spanner and Cockroach for Cockroach DB do it, is they define, more or less there is some uncertainty interval, which is the maximum tolerable clock skew that you can have. Mm-hmm. Let's say you start Cockroach, then you can specify the maximum tolerable clock skew that the machines in your cluster will have. And let's say you set it to 50 milliseconds or whatever. Mm-hmm. It's some configuration value. You say my clocks, or the clocks of the machines in this database cluster, are at most 50 milliseconds apart. Mm-hmm. Then two timestamps that are more than 50 milliseconds apart, they can now be compared, because you have more or less guaranteed that at most they will be 50 milliseconds apart. Okay. So you can compare timestamps of two transactions which have like more than 50 milliseconds difference. For anything that's in between, you cannot safely tell.
Okay.
So you still have this problem there, but for all the rest, which will be the majority normally, you can now make the decision and say this transaction happened before the other.
Okay.
And even Google does it like this. So for Cloud Spanner, they have these fancy atomic clocks and GPS receivers in the data centers. So they have like relatively low clock skew. I think it's just a few milliseconds, like 4 or 5 or something. They still have clock skew. They cannot completely eliminate that, but it's very low. Mm-hmm. But they still have transactions which are affected by that, but relatively few actually, because they have this fancy hardware.
And that means with a higher clock skew that I'm tolerating, the more possible transactions can throw an error.
Yes. So effectively, this means the higher this maximum tolerable clock skew, the more transactions may overlap time-wise. And if they overlap time-wise, you cannot safely tell which one was first. And you have to, if you cannot safely tell that, you cannot make both transactions go on. You have to abort one of them or restart one of them.
Okay.
That means the higher this or the longer this window of clock skew is that you accept, the more transactions you have to abort and retry.
Okay, understood. Okay.
Right, and this is actually what, for example, Cockroach does. They have these timestamps, and they have this configurable window of uncertainty. And if they find two transactions that are like unsafe or whose timestamps are unsafe to compare, they have to abort one of the transactions because they cannot safely tell which one was first. Mm-hmm. So they will abort one transaction and restart it with a new timestamp as of now. And this has the chance that if it's running again and detecting the same or detecting conflicts again, that the other transaction will have actually already finished. Or that if they do it again and again and again, that it eventually will be resolved by one of the transactions finishing.
Okay.
Right. So it will make progress somehow, and they have some. I mean, it's some sort of conflicts for which kind of conflicts they will do what and push which transaction forward. But I mean, normally it will guarantee some progress, right? Mm-hmm. So it may lead to transaction abortion, yes, but you can try again, and eventually it will work. But I mean, it's unavoidable because if you want to, and Cockroach actually, they guarantee linearizability for the transactions. So they have to do all this conflict detection, and yeah, they cannot have all the transactions go on because that would lead to anomalies which are forbidden by isolation level linearizability, right? So they will just bump one of the transactions timestamp and retry. And that's how you can actually ensure consistency, even if you have multiple servers that are involved, which are not really trustworthy in in terms of their clocks. You can still do it at the expense of having to retry some transactions. Isolation is the I in ACID, and yeah, we have to cover this as well because while a transaction is actually running, it must not overwrite or remove data that another transaction may want to see still. Let's say we have a long-running query that is select star from table, and this query will like extract 1 billion records from your distributed database. You can expect this query to run a long time, so it will look at all the records. And if we want to run this query in isolation, there must be no other transactions which actually remove a record from this table while the other query is running. And we must not overwrite data from that table while that query is still running. So we have to protect this long-running select query from other transactions, right? So this long-running select query, it may need to, or it still needs to see its version of the data and its version of the data is the data at the point this query started. It must not change after it started, because even if there's other ongoing transactions that modify the same data, this one query, this one transaction that already started, it must run in isolation, it still must return the correct data.
Okay, so basically I have to, for example, log the whole collection that is being scanned.
Yeah.
Or and maybe in a more advanced setting, just free the documents that already have been scanned by the select query.
Yes, so locking is one solution. So you can serialize these queries actually, or have these queries run sequentially. So first the big select star query and then the modifications. But I mean, let's say the select star query wants to read 1 billion records. You can expect it to take very long.
Yeah.
If you lock the entire collection, you will have one query at a time. You will have this one select star query, which will like run for an hour or whatever. And after that, you will have your other transactions. Okay. It will be isolated, it will be consistent, and everything's fine, but you will only have one query at a time, which is normally not what you want. So there's another solution to that, apart from locking, which is we use some multi-version storage for the data. Like whenever we update a value or we remove a value, we don't actually physically update or we don't physically overwrite an existing value or remove an existing value. But whenever we do a modification to a datum, we write a new record, a new version of this datum somewhere, right? That means when this big select star query is running, it can see all its versions or all the documents or all the data that it's allowed to see. And we can in parallel write new versions of the same keys, which the one query will not see, but only the transactions that created them can now see. And other transactions which are currently operating cannot see them. Because, I mean, we also have this atomicity thing that I touched at the very beginning. A transaction, the modifications of a transaction are not visible until the transaction is committed. That's also something here. So we use the same mechanism here to also ensure atomicity. We write the stuff to multi-version storage, and let's see how this actually can work. So whenever we write a value for the key amount, let's say, we write it to a multi-version storage with the transaction ID and the actual value. And if somebody comes along, some transaction, some query, and wants to know what's actually the value for the key amount, they have to check what version they actually can see. It may be that the big select star query may see the first version, so they may see a value of 10. And that another concurrent transaction has inserted a value of 42. But that value, that version will still be hidden to other transactions until that transaction is committed. And all the transactions that started before, they cannot see that. They will still see the old version of 10. And this is done normally by, you have this multi-versioning data storage. It's also called MVCC, by the way, multi-version concurrency control. So you store every modification with the actual transaction ID or with the transaction that modified the data or inserted the data or removed the data. By the way, instead of removing a datum, you have to store something that is a remove operation, like at the in this table at the bottom, this remove thing. So instead of physically removing something, you store a marker that you want something to be removed. Because there may be some other transactions which still need to see the original value. But some newer transactions may remove that, but you cannot physically remove that until all the transactions are over. Okay, so how is this actually done? So let's see, you scan a table and you find the key amount. What value does it actually have? You have to check this transaction ID here. So for every modification, we note the transaction ID 2. And we have to figure out, because there's now 2 candidates for amount, there's T0 and T1, we have to figure out which of them we can actually see. What we need to do is we need to check transaction 0 and we need to check its status. Going a bit back in mind, we had this slide on atomicity where I said we need to store the status of each transaction in the private section of the key space. And here, this is where we use that. So whenever we find this value of amount 10, let's say, we find transaction T0, we have to look up the status of transaction 0. If it has aborted, we cannot see it. So this value is like, it has never existed, right? We do not see the value of aborted transactions. If it is currently pending, so the transaction has not yet committed, then we may or we may not see it, depending on, I mean, if it's our own transaction, obviously, then we can see this value because we have created that. if the transaction is committed, we have to check if our own transaction has started before that other transaction, before T0 or not. If T0 started after our own transaction, then we cannot see it because it's a newer value.
Okay.
If it was created before, then we can see it.
Understood.
Right. And the same we can do for T1 and so on. And whenever we write a value to this table, we have to check if there's already a value in it, and if we can see that value, or if there's a conflict with any of the values. Let's say we insert a new value for amount, right? We have to check the other two existing entries there, and we have to check if there's an ongoing transaction that is also about, or that also wants to modify amount. And if so, we would have two transactions that override the same key. And one of them would win and one of them would lose, but silently somehow. So we have to avoid this. And there we have to check the status of the other transaction as well. And then we get back to the timestamps of these transactions, and we can figure out which one was first and so on. And at some point, we may get to the decision, okay, this will be a write-write conflict, and we have to abort one of the transactions, simply because they would override each other's data. And then we will deterministically abort one of them, and it may restart later and try again, and then it may actually work or not. But we are done now. So we cannot go on, we have to abort one of them. And this is why we need the central place of transaction IDs and their statuses and their timestamps, because we may need to look it up from all places when we look at the document in our MVCC storage. We need to check the other transaction status, and we need to check, can we see this or not? We need to do this for every read and for every write. So this makes read and write operations a lot more expensive than if we wouldn't do it, but it's unavoidable if we want to guarantee like isolation and consistency.
Okay.
The good thing here is, transaction statuses can be cached quite aggressively. So for example, a transaction that was aborted will never get to pending or to committed. It will only go from pending to aborted or from pending to committed, but never back. So once we retrieve the status of a specific transaction, we can reuse this and cache this forever, right? So it's not probably as bad as it sounds first. Last thing to keep in mind is the durability for the D in ACID. And durability basically means, so we are almost done here. So durability, actually, I take this for granted, because durability here actually means all the write operations that we do in a transaction, they need to be done not only on the leader chart, but we need to wait until they are persisted to at least one replica, or to configure a number of replicas, because otherwise durability would be sacrificed if the leader goes down. And if the leader goes down, if we only write to a leader, then we would have data loss. So we need to make sure data has reached not only the leader, but at least one other replica, and is safely committed there. And then it's actually durable. So a commit can only be considered successful if the leader plus a configured number of replicas have acknowledged the modification, or have acknowledged the transaction commit. This is also true not only for the write operations that we do, but also for a transaction commit. Because a transaction commit will write the status key for the transaction, it will write like committed to that key. And this write also needs to hit multiple nodes in order to be like durable, right?
Okay.
Because if we just write it to the leader goes down, the status of this transaction would be unknown. So we need to save it in at least two places, and then one node can go down, and we still have the status of this transaction and can be figured out later.
All right.
But I think that's about it, how to organize distributed transactions. And that was more or less like a blueprint of how this can be done. I'm pretty sure there's other ways, like I talked about this fauna, or I mentioned this FaunaDB beforehand. They do things a bit differently, and it's also interesting. But this was how it's described here is about how, or I'd say it's somehow like CockroachDB and Google Cloud Spanner do it. And it's definitely something that that seems to work, because these databases are out there and they actually, they actually work. So it's one of the ways to actually achieve distributed asset transactions, but not saying that this is the only way to do it.
All right.
Right. So
okay.
I think I've reached the end. Let me quickly check. Yeah. Okay. So quick recapitulation. So I've talked a bit about like distributed queries, like complex queries for joins and all this, and a bit about distributed asset transactions. And going back to my original slide here, where I said, okay, we initially had this trade-off between NoSQL and highly available and scalable, and complex querying and joins and transactions. This is not 100% true anymore. We have this thing at the bottom now, regardless of how it can be named. We have databases right now that are highly available and scalable, that have transactional guarantees and complex queries and joins. So this is actually there and can be tried out right now. So I think that's then about it from my side. Few credits here. I've used some free icons. I have to give attribution to that. That's on the bottom of the slide. That's one of the requirements for using them. I also have to mention that obviously if you like this talk or if you like ArangoDB, please star us on GitHub. The address is mentioned here. You can also participate in our community survey to win a free t-shirt. The URL is over here. We are also delighted if you could mention us in your tweets, or if you have any questions to us, then simply reach out to us. I think that's about it from my end. Jan, do you have any questions right now?
No, I'm good. Thanks a lot for taking the time to explain to me